So good afternoon, everybody. Time to switch your brain to reionization then. I would like, first of all, to thank the organizers for inviting me to give this review talk on the theoretical modeling of the reionization process. So what I'll try to do is to give first a brief introduction on the ingredients that are needed to model reionization, and then a focus on the main approaches that people are using in the literature to model the process. So basically there are three main ingredients that we need. The first of these is a model of structure formation that we need to retrieve the distribution of gas and of sources. There are various approaches that can be used, semi-analytic. You can run your favorite n-body or hydrodynamic simulation, or also what is typically referred to as a semi-numeric approach. And then we'll come back to all of these later on. And by the way, I would also like to thank Christopher for his review talk, because he's actually covered some of the topic that I was meant to cover myself, but I can focus on something slightly different. So it was a very nice introduction for this additional review, although that was more focused on the galaxy formation rather than on the IGM and the reionization. So the second ingredient that you need is to know which are the properties of the sources of ionizing radiation. Almost, let's say, all of us believe that hydrogen reionization is mainly driven by stellar type sources, but there can be, and there is probably, a contribution also from more energetic sources like accreting black holes, X-ray binaries, or even more exotic sources like dark matter annihilation, decay, cosmic rays, whatever. Just let me say a few words on the stellar type sources. We've heard a lot already today about what we know or don't know about the first stars and their properties. And in general, we don't really know much about really the details, which are nevertheless important if you want to correctly estimate the ionization budget. So this is just a very simple example of a spectral energy distribution of stars which are distributed according to different IMF and have a different metallicity. So in blue you have stars with a solar metallicity and a salpeter IMF. In black, the same salpeter IMF, but metal-free stars. And in red, metal-free stars, but they are more top-heavy. So you see that in terms of ionizing photon production, this makes quite a big difference. And the same applies if, rather than just single stars, which is what was shown before, you consider also binary stars, which recently are attracting increasing attention. These are some spectral energy distribution from BPAS. So if you just concentrate on the left panel here, where we have the lowest metallicities, you can, for example, compare the brown and the red line, where you have binaries and single stars with the same metallicity, or the dark and light blue. And again, you see that there is a difference in terms of ionizing photon production, which clearly has an impact in our modeling. We also heard about this transition between an initial metal-free top-3 population of stars towards a more standard star formation mode, which depends on the metallicity. Now, the problem is that it is really not possible to include all the detailed mechanisms that drive this transition in a completely cell-consistent way in our modeling, so that typically when the transition is included in the modeling, that doesn't happen very often, I have to say, we assume a certain threshold of metallicity below which we have pop-3 stars and above which we have pop-2 stars. And this is just an example from a series of simulations from Umberto, which is quite old, but still very much state-of-the-art, which illustrate my point very clearly. So these are two slices of two series of simulation, hydrodynamic simulation, in which this transition is taken into account and all the primordial chemistry. On the left, you have a case in which the transition is 10 to the minus 3 solar, and on the right, 10 to the minus 6. In red, you have gas below threshold, and in yellow, above threshold. So in this case, a redshift 11, you will still have some pockets of gas in which, in principle, POP3 star could form, while in this case, most of your gas is above threshold, and so your model would just form POP2 stars. And again, this would have an impact in the modeling. And finally, what's probably the mother of all uncertainties is the fraction of ionized photons which are able to escape from the production site into the IgM. And I'm actually surprised that we heard the word escape fraction only a couple of times, because usually there is, it's a topic that attracts a lot of debate and attention, but maybe this can be part of the future discussion. But the bottom line is that both observationally and theoretically, it's a very, very uncertain quantity. So we just use it as a parameter. And I should say that well, if any of our simulator tell you that we resolve the escape fraction, don't believe us, because that's not true. Nowadays, we are really not able to cover all the relevant scales to do that. So this is just to highlight that there are really, at the moment, large uncertainties associated to the properties of the high redshift, the stellar type sources, and the same applies also to other sources, which are not going to touch upon right now, though. And the last ingredient is a way to follow the evolution of the ionized regions. And also in this case, we have very different approaches, from the simplest one, in which you just count how many ionizing photons you have, how many atoms you have to ionize, to the most complex 3D, multi-frequency, non-equilibrium radiated transfer approaches. So that in the end, you have on the one end of the scale, these fully semi-analytic models of reionization, which are extremely useful if you want to explore a wide parameter range and the effect that they have on average properties of the IgM. And at the other end of the scale, you have these radiation hydrodynamic simulations, which include a self-consistent treatment of a large number of physical properties, and then you have all the flavors in between. And I am personally convinced that each approach has its merits. There is no single approach which is ideal, and that indeed they're sort of complementary, and depending on the type of problem that you want to address, you should choose the right approach. So the rest of the talk will concentrate mainly on the simulation part, trying to highlight some of the merits of the various and different approaches. So first of all, a very completely arbitrary nomenclature that I will use. So I'm going to define very large scale, about 500 co-moving megaparsec, large scale between 100 and 500, between 30 and 100 intermediate scales, and then below 30 small scales. So let's start with the radiation hydrodynamic simulation. So in this case, these the three ingredients are basically directly contained in your code of preference. And this is a table containing some of the radiation hydrodynamic simulations that have been run to study reionization. Most certainly not complete, so apologies because of these. And also the numbers that are quoted here might not be completely correct, because sometimes it's not easy to keep in mind all the H, co-moving, proper, or the various transformations. So this should be taken with a little bit of care. So what I would like to highlight here is that most of the, let's say, most recent simulations fall in what I defined as intermediate scale. Several of them are close to 100 co-moving megaparsec, with a resolution that varies between a few 10 to the 5 and a few 10 to the 6 solar masses, various methods to follow the hydrodynamics, and most of the radiated transfer is moment-based, with between 1 and 3 frequency bins. And you know, in this list, I could not avoid to mention what is probably the first of these radiation hydrodynamic simulation by Nick more than 20 years ago, which cannot be compared with the modern simulation in terms of resolution, box dimension, but it really already contained basically all the physics relevant to the problem. But then you lose. You lose with yourself, you know. So, as I was saying, these simulations really include in a self-consistent way a lot of physical processes, and so they also give you an abundance of information on the properties of the IGM and on galaxies, as it's nicely summarized by this figure from the Thiessen collaboration. And indeed, I think that the strength of this simulation is in trying to understand the fact that our choice of parameters or prescriptions, because keep in mind that still simulations, we have to give you know, some input parameters, and we adopt certain ways of treating the physical processes, so that they're not, you know, they have limitations. So the fact that these have on galactic properties, so these are really ideal for this sort of studies. And this is, for example, just a simple example of a suite of simulation SPICE, which have been run recently, the aim of which was to understand the effect of supernova feedback on galactic properties. And these are images face-on and edge-on, composite RGB JWST, Arashi 5, and in the top you have a case in which supernova feedback happens in bursts, so all the supernovae explode at the same time. The middle panel, it's smooth, so they explode according to their age, so different times. The bottom case, it's like the smooth, but you have some hypernovae explosion, so a higher energy. And you see that while you have this less disruptive feedback, you can form nice disks. You have the time to form nice disks. In a case in which feedback is very bursty, instead, this is not able. So really the morphology and the dynamical properties of the galaxies are strongly affected. So indeed, I think, again, that this sort of simulation, especially in the JWST era, should be focused on trying to understand which are the most important parameters, modeling of the various ingredients and what they affect, how these can be constrained by observation, JWST or others. On the other hand, I don't think that they are ideal to probe the larger scale, IGM scale. And the reason for this is, number one, because they are very computationally expensive. So, you know, the dimension of the box is somewhat limited, and also the number of simulations that you can afford to run is somewhat limited. And second, because if you're interested in the detailed properties of the IGM, then in addition to stellar type sources, you need to include also sources more energetic, like black holes or X-ray binaries. And in this case, you need to be a bit more careful in the way you evaluate, you do the radiative transfer. It needs to be more accurate. So for this sort of studies, probably having the radiative transfer done in post-process rather than self-consistently with the simulation is more appropriate. So there is this second category in which indeed the model of structural formation is taken from either N-body or hydrodynamic simulation. And the properties of the sources of ionizing radiation are extracted either directly from the hydrodynamic simulation or are assigned to the halos of the N-body through some prescription, in which the evolution of the ionized region is followed in post-process with your code of choice. And indeed, in this case, again, this is an incomplete table of some of the simulation in this category. You see that most of these simulations fall now in the large category. rather than intermediate that we had before. So they have larger boxes, and the radiated transfer is typically ray tracing rather than moment-based, because it's much more computationally expensive, but it's a bit more, it's more accurate than the moment-based. And also the number of frequency bins that can be used is also larger compared to the moment-based. So just to give you a few examples of simulations in this category, this is probably the largest one, which is based on about 600 co-moving megaparsec M-body simulation. This is a slide showing the density and ionized fraction fields. So these scales are really large enough to capture also the statistics of reionization towards the end of the process, where you have the dimension of the ionized region, which can be tens of megaparsecs. And so from a statistical point of view, it contains much more information, is more accurate than smaller boxes. The author of this simulation also ran a simulation with exactly the same physics, exactly the same parameters, but just smaller boxes, so 160 co-moving megaparsecs. And you see that if you calculated the density power spectrum, this is a ratio 6, they are quite converged. And they are converged also in terms of the evolution of the mass average ionized fraction. But if you look at the more detailed quantities representing the reionization process, in this case I'm showing the volume-weighted PDF of ionized region, you see that you start seeing some differences. So here again is, I come back to my initial statement that depending on the quantity of the problem that you want to address, you should choose carefully the parameters of your simulation and the method to use. These larger simulations are used or have been used also to compare, as I already mentioned, to observation towards the end of reionization. This, for example, is about 200 co-moving megaparsec on a side, and has been used to make comparison with the observed Lyman alpha effective optical depth. Probably Martin will talk about this tomorrow. Because the observed Lyman alpha optical depth is usually given in chunks of at least 50 co-moving megaparsec, then you need to have larger boxes to have a proper or a better comparison. And finally, let's go back to the point of the necessity of including also sources more energetic than stars. This is a series of hydrodynamic plus radiated transfer simulation, showing a case in which we have only stars as sources here on the left. Then you have stars and accreting black holes, stars and X-ray binaries, stars shock-heated interstellar medium, and all the sources together. And the rows refer to H2 fraction, helium-2, helium-3, and temperature. So some of the nuances that you observe here, for example, the warm medium outside of the fully ionized region, or this partial ionized region that you observe when there are more energetic sources, could not be captured with the same level of accuracy if the radiated transfer were done in a less accurate way. In this case, more than 80 frequency bins have been used. So the point that I want to make here is, for example, that if you're just interested in studying full hydrogen reionization, then you don't care about the detail of the spectrum, the accuracy of the radiated transfer, to include also helium. But if you want, for your problem, to have more detailed properties of the IGM, and then in this case, the inclusion of these parameters or extra steps in your modeling is or can be important. So this sort of approaches is really good to study the large-scale IGM properties. But although they are computationally much less expensive than the radiation hydrodynamic simulation that I mentioned earlier, they're still quite computationally expensive. So also these kind of approaches for some problems are not really ideal. I'm thinking about the applications to the 21 centimeter signal observations, which we haven't heard a lot during this conference, but basically it's the observation of 21 centimeter signal from the neutral hydrogen at high redshift is the ultimate probe of the properties of the IGM, because it can tell you really, in principle, the distribution of neutral hydrogen as function of time and space. But thousands of models are required to be compared to observation and do sort of parameter studies, infer all the various parameters. And this is not feasible with this sort of approaches. That's where the semi-numerical simulation started to really give a very important input. And indeed, these sort of approaches were born to address these different observations. In fact, most of the models or simulations for 21 centimeter applications fall in the very large category. And they are based either on embodied simulations for structure formation or perturbation theory. And the radiative transfer is either 1D or the simple counting basically of photons and atoms, because clearly this is much, much faster. So, and actually while researching for review, Andrea, I realized that during my PhD, we might have written the first semi-numeric approach, and I hadn't. It's your fault. And I had sort of forgotten about that. So just again, to give you a couple of examples, this is probably the largest semi-numeric simulation, which is more than 7 gigaparsec on a side. This is a slice of neutral fraction of redshift 8 compared to the field of view of some of these radio telescopes that are aiming at detecting the 21 centimeter signals, so LOFAR, SKA, HERA, and MWA. So here, great statistics on all the scales which are relevant for observations, which is what you need through the whole reionization process. But keep in mind, for example, that these sort of simulations are not really good to study galactic properties, for example, right? So again, it depends on the problem that you want to address. Okay, so this is, as I was saying, because they're computationally so cheap, you can really afford to run thousands of these models. And this just shows an example from the LOFAR collaboration. Here you have the power spectrum of a 21 centimeter signal. The lines are all different models compared to 10 nights of observation. These are upper limits from LOFAR. At redshift 9, and the blue line corresponds to this specific differential brightness temperature map. And as you see, there is already a little corner, so similar efforts are done also within other collaborations, not just LOFAR. So as you see, there is this little corner of models which are already excluded just purely by upper limits from 21 centimeter observations. These are extreme reionization models, but it's exciting that we are getting there. And upper limits are coming down. So actually also soon new results should get out in the literature. And the point is that early in the future, hopefully, we'll be in a situation in which having all these thousands of models will be very useful to do some parameters inference. So again, this is the sort of approaches I'm already done, which is needed or is more useful for application to the 21 centimeter signal. Although they can be used, for example, also as to compare to large surveys as well, keeping in mind again that galactic properties in this case are not as well produced as by for example, radiation hydrodynamic simulations. Okay, so I'm coming to my conclusions. First of all, I would like to mention the fact that I didn't mention at all, because Christopher mentioned them, all these approaches that are emerging in the past few years based on machine learning for example, to artificially increase the resolution of simulation, because also in reionization, clearly what you want to do in principle is to, again, model very large scale, but have a way also of simulating the small scales where all the action happens, you know. So this, I think, is a very interesting development that is happening the past few years, and it's very, very interesting, and it will be very useful. So I hope that I convince you that there is a wide range of different approaches in the literature which you can use to model the reionization process, and that you know, they all have their merits, and depending on the problem that you want to address, you should try to choose the right approaches. And yeah, that's it. Thank you.
We are open for discussion. Joe's going to go first here. Grab that one.
Great presentation, and I really liked how you broke things down across the different regimes. So in the post-reionization IGM, we also want to do parameter inference, but we can't, because that large box, but resolving the IGM regime, is still only being done with one simulation. Yes. So is that purely because of computational cost, or is there something else going on? Like, why do we not have 20 reionization models like the Kulkarni or Ilyev models that you showed?
Well, in principle, you can have 20 reionization models also with, I mean, probably not with the radiation. Well, with the radiation hydrodynamic simulation, you can probably do that, right? Because if you want to, well, if you want to model 200 co-moving megaparsecs, no. But another option could be to go a bit smaller and then do sort of composite, right? Flipping the boxes to artificially increase. So you could do that, but still they're very expensive. Recently, we have run some of these radiation hydrodynamic, hydrodynamic simulation with the radiated transfer in post-process. And we have about 20 reionization histories. And these were done with Sherwood type of simulation, which are ideal designed for IGM studies with the radiated transfer in post-process. So that's feasible. But I don't think that the numbers are still high enough to do inference studies, right?
20 gets close if you build a good emulator, but yeah.
Yeah, you need to increase them or choose the parameter space well enough that then you can build some emulator. And oh my God, sorry, I forgot that. She's in Leiden. Yes, exactly. Caitlin, right? She's working in this direction. So
that's true.
Yeah.
But I'm an observer.
Yes. So she's working in this direction, and she's coming to MPA. I'm very excited to have her around. Yes.
I was actually going to chime in. So thank you, first of all, for the great talk. I don't think we actually need to emulate. I think what we need to understand, right? So if you think, to look at redshift 3, right? You show the laminar forest at redshift 3, you can actually say everything about laminar forest. You know what density is coming, what temperature density relation is. You can measure the pressure smoothing length. You can probably constrain fluctuations in ionizing background. We actually know everything about this forest because we have the complete theory. I can write you a set of equations that describes the full spectrum. But if I now take 5.5 redshift spectrum and I see the spikes, I have no idea, right? So what densities, temperatures, what kind of fluctuations in the ionizing background I need. So I think what we need now is to actually understand what those spikes tell us about the underlying physical conditions. And then we wouldn't need 20 simulations because we can just write an analytical one equation that does it for infinite number of simulations.
I'll let you take that one.
No, but it's completely true. It's completely true. I mean, that's why I really advocate to to try and use the simulations, not just to reproduce observations, because in the end, you can tweak your parameters in a way to reproduce stuff. You need to use simulations to understand what's the impact of different quantities. So running simulations just for the sake of having, 1 megaparsec larger than the previous one or one extra particle, I don't think it, personally, this is my view, I don't think it's very useful. I think we really need to concentrate on what is important and what is the effect of the various components.
So since we have the first numerical simulation and the first semi-numerical model, so what have been the main surprises, in the progress? So if we take your models from 2000 or so, what was not present in those models that you really needed something much more expensive? No, I think that, I'm really curious,
yes,
because
it is a very important point. I'm laughing as well because, for example, since I started my PhD, we were talking about feedback. What have we learned more about feedback? I mean, something solid, right? I don't know. I mean, from one point of view, it's good because it means that we can keep working on that. But from another point of view, it's a bit depressing. Yeah. So, there are, I think, indeed some aspects that we haven't. I mean, we have made progress in the way we are able to describe the details and also clearly, the larger computational power that we have access to, so we can model things much more in a much more refined way. But yes, go ahead.
Just an addendum to what Benedetta just said. I think that for me, the main difference is that we did understand what we were doing because the thing was simple. Now I'm not sure I'm understanding all the details of the most advanced study that we have. And so that is the difference. And I don't know I have no solutions. But.
And actually another thing that when this all started, there weren't many observations, right? So we could play around more. Now we have some observation, and also, as Andrea was saying in his talk, we need to be able somehow to reproduce them. But I don't think that just reproducing them tells us, again, we need to reproduce a number of them and try to understand the whole puzzle, because reproducing the UV luminosity function at various redshifts, I can do that, other people can do that. What do I learn? That there is a combination of parameters which reproduces it. And testing, absolutely. But the thing is that indeed there are, the observations are building up. Hopefully when the 21 centimeter will put more stringent constraints, that there we'll really have much more knowledge, at least on the IgM, like the amount of neutral hydrogen, or the dimension of the H2 regions. This sort of information will be very useful. But it won't be the whole, sorry, interrupt me if I'm talking too much, but this is, another thing, for example, that comes out often is, can 21 centimeter observation observe ionized regions at high redshift? Yes, in principle it can. Can it distinguish if it comes from a quasar or galaxies? My answer is no by itself, because if you model it, just the H2, the ionized region from a bunch of galaxies can be very similar to the one produced by a bunch of galaxies and a quasar. So you need that in combination with other things. But I think that, little by little, we can build a puzzle.
We have a question in the back.
Thanks for the amazing talk. I had a question about, so you showed this volume size distribution and
Yes.
going from 500 megaparsecs to 160.
Yeah.
And how you really don't capture those, the largest bubbles, essentially.
Well, this guy here, yes.
So my question is, given that we know the big impact that reionization has on the faint end of UV luminosity function and dwarf galaxies, etc., how do we link these very large-scale bubbles to the physics of the smallest galaxies at high redshift in a self-consistent kind of way?
That's a really good point. And I think that maybe here really these also machine learning approaches can help, right? So we can try to run simulations which are consistent with each other in terms of physics and methodology at different scales and resolution, and then try to bridge them or put the information together with with the aid of some sort of machine learning or something like that. Because I don't think that as of now we are able to really model property, cover property, all the scales that are relevant for this study.
Okay, we have time for one more question before the session discussion.
Benedetta, very nice review, and given that you brought it up yourself, I'm going to ask you, given that simulations are not able to model escape fraction, and given that studies of what escape fractions can depend on, they can depend on various galaxy properties, and given that we don't know the potential contribution of AGN and their escape fraction, how much optimism do you have going forward in terms of nailing down the process? Or what observations do we need to nail it down, or what theory developments do we need? Maybe it's already discussion.
I don't know if is Piero around. I don't know. Because he was making a good point, right? He was mentioning the fact, why would people accept reionization histories driven by stars for which the escape fraction is incredibly unknown? So in principle, it could be between 0 and 100. Why couldn't we study something or accept something which is in principle simpler? As indeed we don't know either the escape fraction from quasars, but we know that it's closer to 100%. At least all the studies on escape fraction of quasars give typically something above 70%. Having said that, I honestly don't know how we can pin down the escape fraction, and if we'll ever, again, maybe also in this case, at least from a theoretical point of view, for me, the only way of doing it is to, again, connect simulations on molecular crowd scales that give you the value of the escape fraction at the smallest scales. But again, that will depend on a huge number of parameters, and then build up simulations on larger and larger scales, and somehow find a machine learning approach to describe. In this, I think I'm not a big fan of machine learning in general, but I think that in some cases it can indeed be useful. To connect, to find connections that we can describe with. That you don't understand, exactly, because a lot of people in the audience have worked on escape fraction, and how do you summarize the dependencies of the escape fraction on various scales and physical properties? Not easily, right? So, yeah. Thank you.
I take that Thank you again for a very nice review, Benedetta.